Hello everyone, my name is Sheng-Feng. My advisor is Professor Wei Chen. My research topic is semi-supervised anomaly detection. What is anomaly detection? Anomaly is the sample that is different from most other objects. So once you want to define anomaly, you need to define normal object first. Anomalies are also referred to as outliers, novelties, and noise. And anomaly detection, AD, is the process of finding anomaly. The ratio of anomaly is usually small or equal than 5%. Anomaly detection is applicable in a variety of data domains, like tabular data, time series, and images. For example, fraud detection finds the crime from tabular record. Most of records are normal transactions. Only a small fraction of record belongs fraud. Another example is detecting anomaly from IoT sensor data. And sensor data is a time series. We need to find anomaly from its time domain, time neighborhood. Another popular topic in industry is defect detection. It usually detects anomaly from an image. And as you can see, the first row is normal image, and the second row is the same product with defect. Like here, a white dot, and here the pillow has a white dot. Yeah, that's a defect. And the third row is the run-in of the defect. There are three types of anomaly detection. The first one is supervised anomaly detection, and the second one is called semi-supervised anomaly detection, and the third one is called unsupervised anomaly detection. Supervised anomaly detection requires the training data set that has label instance for normal as well as anomaly cases. So you have two classes in this setting, and the key difference to many other statistical classification problems is anomaly detection has imbalanced class distributions. The ratio of anomaly cases is usually less than 5%. And then semi-supervised anomaly detection uses training data has labeled instance only for the normal class. So there is only normal class in your training data without any outliers. Only model the behavior of normal data. And in my personal opinion, this property is very important because anomaly usually has high variation and unpredictable. If they appear regularly, we would not call them anomaly. So we don't have any assumption in this. We don't have any assumption about anomaly in this problem setting. The third one is called unsupervised anomaly detection. In this problem setting, it does not require any training data. We directly detect anomalies in an unlabeled test data set. So we have only one data set, include normal data and some anomaly. We want to find anomaly in this data set. Okay, in this talk, I will focus on image data. So here I give some application on image data. First application is remote sensing. For example, after disaster, the government wants to statistic the total damage of their building. So it takes a lot of pair images and it wants to identify whether buildings have been washed away by tsunami or not. And on the right hand side there is an example. The left image is before the tsunami and the right image is after the tsunami. Okay. And the second example is medical image. We can detect disease from a clinical image. Like here, a chest X-ray image. We can segment or classify whether this image is normal or abnormal. And next is surveillance. Like this image. This is X-ray security screen image from airport custom. In this red rectangle is an illegal item. And as we know, illegal item is rarely shown. So we cannot label many illegal items to do classification. So this is an anomaly detection problem. Okay, next I will introduce some basic idea of semi-supervised anomaly detection. The first is reconstruction-based method. This idea often combined with generative model, like autoencoder or GANs. We train on normal data, then we assume the model only generates normal images. After we get our trained model, we can select anomalies based on the reconstruction error. Because this model only trained on normal image, so the intuitive behind this method is the reconstruction error of abnormal image will be large. And the second idea is classification-based method. The spirit behind this approach is that they want to learn a good representation from normal data, so they can separate normal and abnormal based on these good features. The separation between space region contain normal data from all other regions. So we separate our feature space into 2 or more regions, and one region containing only normal data, and other regions is for our anomalies. And the two classic technique of this method is one class classification or self-supervised learning. Okay, first, I will introduce reconstruction-based method. An autoencoder is one of the most well-known deep generative models. It contains two parts, encoder and decoder, or generator. An encoder maps input image to latent space, and decoder maps latent space feature back to input image space. And we want the output is the reconstruction of input. So an autoencoder reconstructs input itself. And we usually use mean square error as the loss function. Okay, so autoencoder learn a meaningful latent representation without any supervision. It's an unsupervised learning method. And next, GAN. GAN Generative Adversarial Network, also called GAN. GAN consists of two networks. One is generator and another is discriminator. Generator maps a noise from latent space to data space. Discriminator learns to distinguish real samples and fake samples. We train discriminator to maximize the probability of assigning the correct label to both real example and fake examples from generator. In other way, we simultaneously train the generator to minimize this term log 1 minus d of g of z. That is maximize the probability of g of z. So the generator wants to generate a realistic image to cheat the discriminator. Okay, so D and G plays the two-player minimax game with this value function. Okay, here comes our first anomaly detection algorithm, Anomaly. And Anomaly combine autoencoder and GAN. And in their problem setting, all of trained data are normal examples. So this is an semi-supervised anomaly detection algorithm. And here is their model structure illustration. Here they use an autoencoder and concat followed by a decoder. And there is a discriminator to distinguish their reconstruction and raw input. Okay, there are three loss functions: contextual loss, encoder loss, and adversarial loss. Contextual loss, it makes reconstruction similar to raw image. The reconstruction is denoted by x hat, and raw image is denoted by x. And this loss is distance between x and x hat. So it will let this autoencoder to reconstruct x. Okay, the second loss, encoder loss, let the second encoder learn to encode normal image. From our assumption, the autoencoder only generate normal image, no matter its input is normal or abnormal. So the second encoder only encodes the normal image to latent space. Okay. The third loss, the adversarial loss. This loss guides the autoencoder by the difference between internal feature of raw images and reconstruction. On the other hand, we can adjust discriminator to distinguish real and fake image by cross entropy. So this is a GAN structure with an autoencoder with additional encoder. Okay, after we get a trend model, we can start to infer our test data set. If X is normal, then through the autoencoder X hat is also a normal image. And through the second encoder, the Z hat will close to Z, right? Because X is a normal image. So X hat is also a normal image. So Z hat and Z are both features of normal image. So Z will close to Z hat. On the other hand, if X is anomaly, then through this autoencoder, Z hat will differ from X because this autoencoder only generates normal image. So X hat will differ from X. So the Z hat will far away from Z, right? This is the feature of normal, and this is the feature of anomaly. Okay, so let's define their anomaly score as the distance between Z and Z hat, two latent features. And because the distance in input space is easily affected by small noise, so it is usually more robust in compare the feature in latent space. Okay, the second idea, classification-based method. To start this part, I need to introduce self-supervised representation learning. Self-supervised learning is one of unsupervised representation learning. It learning meaningful feature without any human label. Okay, for example, predicting image rotation. For every image in dataset, we can duplicate every image by 4 transformations, like 0, 90, 180, and 270 degrees. Like this figure, for any image, we can produce 0-degree image, and 90-degree image, and 180-degree image, and 270-degree image. And because we know what transformation was applied on this image, what rotation degree was applied on this image, so we can give every image a label. Let's say 0 degree is Y is 0, 90 degree Y is 1, and Y is 2, Y is 3. So we have a image and label pair, right? This is a supervised data set. So we can train a convolutional neural network to predict the rotation in a supervised manner. Okay, and we only give this model images without any label, and it labels itself, right? So it is an unsupervised learning, but we train this model in a supervised manner. So this family of learning algorithms are called self-supervised learning. Model supervised itself, so it calls self-supervised learning. Okay, now we know what is self-supervised learning. The next question is, why does it able to learn representation in this way? Okay, there is an intuitive way to think about this problem. Okay, now we train a model that is able to recognize the rotation transformation. And how does human know the rotation degree on an image? I guess the answer is here. Look this image. Yeah, you know there is an object in the foreground. Yeah, right. It's a bird, and you know the shape of bird and the location of this bird. And you can look the first image, and you know the first image is rotation 90 degree from the second image, right? Because you know this bird is stand this way, and if you rotate 90 degree, and the image will become the bird will become this. Okay, and once you can recognize the rotation degree, you must know the type of the object, the shape of the object, and the location of the object, right? So the model will be required to understand the concept of the object depicted in the image, like type. There is a bird in the foreground and it stands on a branch, the pose. The location, this bird is in the center of image, and the shape of bird. Okay, so the model learned the type, the location, the shape of the object. So this is a good representation of an image. Okay, based on the self-supervised learning, we can introduce our second anomaly detection algorithm. Anomaly detection uses geometric transform, or called geo-anomaly detection. They use self-supervised to learn representation, and they use rotation, shift, and mirror transformation. Rotation 0, 90, 180, and 270 degree. There are 4 transformations, and shift along x and y axis for minus c0 plus c, minus c0 and c pixels, and horizontal flip or not. So there are 4 times 9 times 2, 72 transformations in total. And their detection algorithm is straightforward. First, we train a classifier on the transform train set. So we have a model. It can predict what transformation was applied on the image. And this model outputs the probability about transformation. And they approximate the probability to be a Dirichlet distribution for each transformation. This is called post-processing, just a parametric distribution approximation. Yeah. Okay. And then once we get this Dirichlet distribution and a trend model, we can infer our test set for each image in test set, and for each transformation Ti, I is 1 to 72. And we can get the softmax probability y of Ti of x. Y is softmax probability. And then we have the Dirichlet approximation. So we can get Dirichlet likelihood called P. And let's detect anomaly based on the score function n. N is written in this form. Summation log P, and P is PDF of Dirichlet. So log PDF, summation log PDF is just the log likelihood of the Dirichlet transform. Okay, and why this score function work? For each transformation, the authors used a Dirichlet distribution to model its normality. Right? So we have 72 Dirichlet distribution approximation. And because our model only trained on normal data, so this Dirichlet distribution only model the behavior of normal data. And they define their score function as the product of all density function, maximum likelihood. Okay. And if an image has higher score, then this means this image is more likely normal, right? Okay, this is intuitive. And here comes the experiment result. They did the experiment on CIFAR 10. CIFAR 10 has 10 classes, so we can create 10 different experiments. Every experiment uses one class as single normal class in this experiment. So for example, experiment 0 use class 0 as inlier. Experiment 1 use class 1 as inlier. So the training data has 5,000 images, only one class. And test data consists of 10 classes, and there are 10,000 images. And here is the AUC result, AUC score of our first algorithm and second algorithm. As you can see, the second algorithm outperforms the first algorithm on this data set. Okay, next is our proposed method. Okay, first we do the simple analysis on the latent space of geometric anomaly detection. Here is our observation. Features of inliers should be grouped together in the embedding space, in the Z space. And intercast separation is larger than intracast separation, right? Because GeoAD do a classification of for every transform. So it can separate every transform and group the same transform together. But the problem is that outlier, if the input is outlier, then the feature of outlier will locate on a strange location, and there is no guarantee low likelihood because this is extrapolation. Next, the model may know the rotation from background, so maybe it will not learn the shape, the location from object. It learns features from background. As you can see, we can know the rotation degree from land and sky without knowing anything about this object. Okay. So based on this observation, we propose our approach. We combine autoencoder and self-supervised learning. First, if outlier is isolated, so we can project outlier to normal manifold. And because within this manifold, autoencoder only reconstructs inlier. So if an outlier is projected to normal manifold, it will reconstruct very bad. And second, if the model knows its rotation from background, so this outlier will locate on the normal manifold, so it will reconstruct bad. Yeah, so our idea is very simple. And on the bottom is our model architecture. We use 3 loss functions. First is classification loss. Is to train the classifier to predict transformations. And the second one is reconstruction loss. Is to train the autoencoder to reconstruct T of X, the transformed image. And the third one is feature reconstruction loss. It's like an autoencoder inside a bigger autoencoder. Once we get Z, we want to project it onto normal manifold. So we train another autoencoder to reconstruct Z. And because this this autoencoder only learn to reconstruct normal feature. So this Z hat is on the normal manifold. Okay, so here is the result, and all experiment setting are the same. And here is our AUC, and as you can see, our AUC score is better than GeoAD by 0.01, 0.015. Yeah, only slightly improved GeoAD. So we are still looking for better method, like better model architecture or better projection method. And the summary, we combine two different ideas, reconstruction and classification. And our approach improves AUC by 0.015. We are still looking for better model architecture to improve this number. And we also want to try nonlinear projection rather than linear projection. Okay, this is my presentation. Thank you for your listening.